Alright guys, so in this recording we're going to be looking at the halogenation of benzene. Alright, so the halogenation of benzene. Alright, really simple, the halogenation of benzene. Now we're going to be specifically looking at the reaction bromination. And you know, from bromination you can get your chlorination, fluorination, whatever you need, right? Bromination is just it using bromine. Okay, now the mechanism specifically would be an electrophilic addition. After all, benzene is a unsaturated compound, right? So it is unsaturated. We're going to use one specific conjugation of benzene. Specifically, we know that they exist in different structures like this. Let me just draw that up real quick for you. They exist in different structures where their double bonds are located in different places. But I'm just going to use one conjugation, right? Okay. So we know that bromines are aromatic compounds, right? And what this generally means is that it has a ring structure. It must be cyclic. Its carbons must be sp2 hybridized, right? It must have a flat or a planar or near planar structure, right? And it must have the free p electrons moving around, free electrons constantly moving around to create a flowing ring system, right? So even though benzene is unsaturated, right, and it happens through electrophilic addition, it doesn't just go through electrophilic addition like that. You can actually have a reaction in which something like this occurs. You can't have that, right? We must be able to create a strong electrophile. This is because of the stability of the benzene ring. It's so stable that it can't just be destabilized by electrophiles, right? Some persons may say that, wait, but benzene has a high electron density on its ring system, but it's really stable. It won't allow for that type of electrophilic addition. So what we're gonna need in this case is what we call a Friedel-Crafts catalyst. So the first step one, is involving the activation of that catalyst. So activation of the Friedel-Crafts catalyst. Alright, and this is a Lewis acid. Alright, in this case we're going to be using FeBr3. Alright, so let's look at the activation of this catalyst first. So this is the catalyst that we're working with, right? It has a positive center, slightly positive center around the iron. Alright, now we're going to be using molecular bromine because you know we're looking at the bromination specifically. What we're going to have is the donation of a pair of electrons into that system, right, to activate this catalyst. So what this catalyst is basically doing is acting as a halogen carrier, right? So what results from this is really a structure. Let me do it laterally, right? What results for this is our structure like this, okay? We're gonna end up with iron bonded to bromine in its regular FeBr state, but it's also bonded to the molecular bromine like this. So this group gets added on here, okay? So it creates a structure that looks like this. Let me just add in some free electrons so you can understand how this works. So there's a slightly negative charge there, right? We're gonna have a slightly positive charge here. We're gonna have a slight positive charge here, right? So we're not gonna get into the entire electronics of the system, or well, the electron placements in the system and everything like that. But what we're seeing is that bromine now has a slightly positive charge, here, right? It makes it a much stronger electrophile. So the purpose of the Friedel-Crafts catalyst is to act as a halogen carrier and in order to create the strong electrophile, right? So with the creation of the strong electrophile here, what is step 2? In step 2 now, we're gonna have our benzene. Alright, now that we already created the strong electrophile, all we need to do is add it to our system. Alright, so we have benzene like that. Let me draw everything so that you guys can see how the mechanism works. Alright, so we're gonna have something like this. Just redrawing everything. This is slightly positive. Alright, so since it's slightly positive and it is an electrophile, it's gonna be attracting a bond pair. Right? So it attracts a bond pair from the double bond, right? From the ring system, some electrons from the ring system, and then this bond will break heterolytically, right? So we're gonna have a bond breaking like that. So this is how it works specifically, and what we end up with is an unstable intermediate. Alright, so we're gonna have bromine being added here based off of where we put the bonds, where we take the bond from. We're gonna have bromine added here, and we know that hydrogens exist on the ring like this. Now what our issue is that we know that we have a general ring system, right? And we know that one of the main characteristics of aromaticity is that our carbons must be sp2 hybridized. When the electrophile adds onto the ring, the carbon now becomes sp3 hybridized, breaking aromaticity, right? So it breaks aromaticity. That's how I'm gonna put it. Aromaticity, right? It breaks aromaticity, creating an unstable intermediate. Now, what's gonna happen? What is gonna happen here, right? In this case, now we're gonna have multiple variants, right, of the same structure. So because the ring system has been broken, the electrons will now move to actually dampen that positive charge, right? The positive charge that we see here. So what we're gonna see, we're gonna be seeing the positive charge moving around the ring system, right? So the positive charge is constantly moving around the ring system. The electrons constantly move to try to satisfy that positive charge. And each time the electrons move, the positive charge moves to a different carbon, right? So we're gonna have the creation of these unstable intermediates, right? And the only way to stabilize the ring is to return the carbon here on these intermediates back to sp2 hybridization. Now, how are we gonna do that? Or how does this happen? Let's have a look at it. Alright, so let's have a look at how this happens. We're gonna have one conjugation, right? So we're gonna have one of the intermediates. I'm gonna be using the first intermediate that I had, and hydrogen, right? So what's happening here, right? Or let's look at what's gonna be happening here. Let me fix up my bonds, right? Remember that the Friedel-Crafts catalyst exists, right? So remember that the catalyst still exists within solution. So this is the third step specifically, right? So this third step, step 3, is what we call deprotonation, right? Deprotonation, right? So we're gonna have deprotonation happening, and we know what a proton is, right? So the deprotonation of the ring, right, will occur when the hydrogen leaves as a proton. So what's going to happen is that the bonded electrons in the carbon to hydrogen bond will be redonated to the ring in order to dampen that positive charge. We can see that there. And then when the hydrogen leaves as a proton, this proton is going to be added to the bromine, right? So we're gonna have the hydrogen leaving, right? Let's put the bonds on bromine, right? We're gonna have that happening. So the bromine is gonna be attracted to the hydrogen, and when the bromine is dragging the hydrogen off of the ring, the electrons in the pair between hydrogen and carbon right here is going to be donated back to the ring. All right. So what are the products of these in step 3 now, right? What are gonna be our products? We're gonna end up with something that looks like this. We're gonna end up with what we call bromobenzene, right? And then the hydrogen and bromine here will react to create hydrogen bromide, right? As the bromine leaves that ring there. Specifically, the electron's going to be attacking the hydrogen. So I put the arrow in the wrong place a while ago. So looking at this now, the electrons actually come from the bond here, right? And bond there. So it breaks this bond, creating hydrogen bromide. And then we end up with the Friedel-Crafts catalyst at the end of the reaction, chemically unchanged. And that's what the catalyst is. Okay? So those are the 3 steps for the bromination of benzene. First, we have the activation of the Friedel-Crafts catalyst, which is our Lewis acid, right? In this case, it is iron 3 bromide, right? And then here we have in step 2, we have the interaction between them, right? So this step 2 is what we call the electrophilic attack. All right, so the electrophilic attack, and that creates unstable intermediates as the positive charge is going to be, try to be dissipated or diminished by the movement of the electrons in the ring system, right? And in order to completely stabilize the ring, we're going to have deprotonization, right, which returns the carbon back to sp2 hybridization. So when it had these here, it was sp3, right? Now when it loses the hydrogen, it has returned to sp2, right? And aromaticity has been restored. So we have there now, and this is the creation of bromobenzene, the bromination of benzene. That is it.